Functions that involved integrals, and the one that we were using was this amount you had eaten at some point in the day. And the way we defined it was at first we wrote an expression for the amount you had eaten at 6 o'clock at night. And the way you can find that is if you know how much you had eaten at 0 at midnight, plus the net change in the amount eaten, in other words, how much you eat between those two times. That's what this is, right? If you know the amount at a certain point, plus how much it changes between that point and the time you're interested in, that's what that is. Now we extended that to make this a variable. Right down here, we said if we want to know the amount at any time t, this is the variable here. Okay, the variable is the upper limit of integration. So if we know how much you have eaten at whatever time that is, 0, plus the net change between 0 and that variable, you need to do the integral of the rate. If you do the integral of the rate, it gives you the net change, right? Integral of the rate is the net change here. And then this, of course, was just some other variable we used, a dummy variable. All right? So that was the first thing, is looking at the function, writing a function when it's in terms of involving an integral, right? So we had this crazy thing, right, that this is starting at some point here. We started it at 0. And then we added how much you'd eat, and you're constantly eating. I know that that's maybe unrealistic, but you're constantly eating. And then you slow down for a second. And then you will stop there before. Yes? Hey. If you have questions, that's fine. Take your conversation somewhere else if you want. Yes? Well, it's in real terms, I guess it's, I don't know if this allows me to go here. I mean, I suppose if you're thinking of our situation, it's going back in time, which makes the thing negative, right? If you go, I mean, if this is a positive integral, you've eaten a certain amount. If you say at 5 o'clock, this is how much had been eaten. If you make the upper limit before that, it's a negative net change because it's going back in time, right? It's a negative integral if you go backwards like that. The big thing, or the fundamental theorem of calculus now, is asking what is the derivative of that function that involves an area, involves an integral. What's the derivative of the integral of some function? The integral is the area underneath here. We wrote, now this just says area of x is a up to x, so wherever a is here, we could define our function. I mean, the only difference here is I don't have that starting value. Okay, like in before, it had a starting value plus this integral here. And the other problem is I'm using x as the actual variable, a is a function of x. And just to confuse things here, t is the dummy variable because it's just some other variable. Doesn't matter what's used. If you have a function that's the area under a curve here, the one we started before, it started at 0. And we want to look now at the rate of change of this. Okay? The rate of change of this. Look at how fast the area is going up. If I try to move this at a constant rate here, what happens to the rate of change here? Well, it becomes negative over here, and it's positive and stuff. We can have an instant replay of that. Where's the fastest it's increasing? Right there, right? And then it's not increasing for a split second there, and then it's actually decreasing. It's got a negative, and then it's going up, and it's going down. It actually has, the rate of change of this thing is actually connected to the height of that line, right? The height of the function itself at any particular moment. The rate of change right there is 0. The height is 0. The rate of change is at its maximum right there. The height is at its maximum. The rate of change is positive. It suddenly changes to negative. The rate of change is the length of that red line. It's the value of the function itself. Okay? The rate of change does not matter where you start. I could start at a different point here. A could be something else, but that's not going to change the rate of change. If we go back to the amount you've eaten example, it doesn't matter where we start measuring it. Okay, if you flip back over here, we could have equally well said, I'm not going to start measuring at midnight. I'm going to start measuring at 6 o'clock in the morning, and then make this a 6. It's going to change the two values that are involved here. But then if we ask, what's the rate of change of this overall function, right? What's the derivative of this function? It doesn't matter where you start. It doesn't matter where you start here, right? It's just going to be the height of the function itself. Instead of scribbling on there, I should start writing again here. If you write out some function that we had e of t was, we wrote it as e at 0 plus integral from 0 to t of e of u du. But you could make this now some other value. It doesn't matter where you start. This could be at 6 and measure from 6 to up there, like how much you'd eaten at 6 o'clock in the morning, plus however much gets eaten between 6 o'clock and whatever time you're looking at. These two values are going to be different depending on where you start and what point t is. But the rate of change of this, if you want the derivative of this, if you want d dt of this is going to be 0 because it's a constant. It's the starting value. And this is going to be what? Actually, I should have put a little tick mark in there, right? I forgot my little tick mark. That was a problem.
Oh, now it makes sense. Yes.
Well, it's the net change is the integral of the rate of change, right?
Oh, okay.
That's why that has to be a tick mark in there.
Yes. Or you can use the R.
I think it's better if we look at it visually here. Let's go back to this. The function we're writing here, so maybe let's just take the minute to get comfortable with this, and then we can leave the other notation here. The function here is the area underneath, right? This a of x is the area underneath. F of x is the actual curve, okay? F of x is the actual curve. A is the area underneath the curve there. A is the area from A to X. X is the variable. T is just a dummy variable. It could be a U or whatever you want here. Something else, W, whatever. It starts at A and it ends at X here. The area underneath the curve. The value of this function is this area here, right? The area is increasing. It stops increasing. It keeps increasing, and then starts to decrease. The value of the rate that it's changing is this height here. Okay? The rate that it's changing is this height. In other words, the derivative with respect to x, this variable, of that area function is just the height of the function at any given time. The derivative of the integral of f is f. Okay? Go back here and write it out here. There's a picture on here. Okay, there's a picture on here. This function here is, the area underneath here is this function right here. If it makes you more comfortable, instead of t here, you can put a w or something like that as a dummy variable. It doesn't matter which one you're using there. If you'd rather do that, dummy variable. A variable just to stand in there because x is the variable in the function, right? It's the thing that's changing. This, like before, is the thing that's moving. This is fixed here. That's where you're starting. The area function is integral from a to x of f of w dw or whatever, right? But now what we're asking is, what's the rate of change of that? How fast is that changing with respect to x? So we're looking at, what's the derivative with respect to x of this? How fast is that changing? 10 minutes, thank you.
You can wait 8 seconds. You can wait like 40 more seconds. Can you wait till 10 minutes to say 10 minutes?
I wanted to stop it well in the back. So
10 minutes!